All right, hey guys, I'm gonna go grab my laptop real quick. Just a second. Okay. Indeed, the final is cumulative, Lauren. So it's gonna be like heavily weighted towards the newer stuff. I think a solid like 40+% will be newer material since the last exam. So the vector fields, line integrals, surface integrals, the integration theorems, that sort of thing. But we are having material from the older exams as well. As you can see on the final exam review stuff, there is stuff from all the older exams. Yes, Marissa, I will be posting that. I meant to post the other stuff last night, but I used the Notes app in my phone to scan it, and then I sent an email to myself, and it literally took 2 hours to receive that email. It was crazy. So I should probably find something else, some other app to scan that, because that is ridiculous. So let me hang on. I mean, that should give you a good idea of the sorts of stuff you need to know. I hesitate to say that is it, but let me check something. Okay. Okay. Yeah, it's largely going to be that type of material. So the partial derivatives, double integrals, triple integrals, polar coordinate, cylindrical, spherical, optimization stuff also. Yeah, this should be a good guide on the kind of stuff you should focus on. But yeah, I will be posting the solutions for 1 through 11. Yeah, and I'm gonna try to. Good Lord, I was writing up the solutions for the homeworks as well, and I will have those posted as well. Any other like general questions about the exam before we start looking at specific questions? Did everyone get the email I sent out the other day? Just making sure. So you'll have 100 minutes. So did everyone get the email where I gave you the time slots and said you'll have 100 minutes to do that? I think that's all I was told. Let me see. Like I don't have the exam ready for import yet, so let me see. It doesn't say how long the window is. I'm not actually sure. It doesn't actually say how long the window is. So I'm not certain. Yeah, I'm not 100% sure. Ryan, sorry about that. Any other questions? And I'm not sure how many questions exactly are on the exam, but that's never like the greatest. It's difficult to judge the length of exam just by knowing the number of questions. Because of course, a lot of them could be just like set up the integral, or you're gonna have to go through and do the entire integral, or some could be like true false, that kind of thing. So hard to judge, but it should be yeah, I would expect something about 1.5 times as long as the other exams. Anything else? If not, we can look at some questions. Okay, so what questions would y'all like to look at? Number 10 on the review. Okay. All right, so number 10 asks us to calculate the surface area of a piece of a cone. Let's calculate the surface area of the cone. Z is equal to square root x squared plus y squared, where z lies between 0 and 3. Okay. So this we do. I mean, there are a couple ways to do this. We could directly use cylindrical coordinates, or we could use the graph of a function and then switch to polar later. I think this is a lot easier to do. Let me just say in general, so if we have like surface integrals or graphs of surfaces, I would say always use cylindrical to parameterize cones. That is almost always the easiest way to go. I would say unless, so the only exception would be like if you're doing like triple integrals over, say, like ice cream cone regions, so regions bounded by cones and spheres. But I would say by far the easiest way to go would be to use cylindrical coordinates to deal with integrals involving cones. Unless, of course, like you have like the ice cream cone, like the region below like some sphere and above some cone or something like that, then you would want to use spherical. But in general, cylindrical is going to make your life a lot easier. Okay. So that's a note, something to note here. Okay, so areas, of course, we'll call this cone S. The area of a surface is, of course, just the integral over the surface of 1 with respect to surface area. Right. So the area of a region D in R2 is the integral of 1 over that region D with respect to area. The length of a curve is the integral of 1 over that curve with respect to arc length. The volume of a region in R3 is the integral of 1 over that region with respect to volume. Area, volume, length, all that stuff is just you're integrating 1 with respect to whatever the thing is over the region. Okay, so we're doing a surface integral here. And so we need to parameterize our surface, et cetera, et cetera. So let's parameterize S. Just a little sketch here, although it doesn't have too much in this case. That's C equals 3. So that's our surface S. Okay. So I said we should use spherical here, or sorry, cylindrical coordinates to parameterize this guy. And so that means we're going to let x be our cos theta, y be our sine theta, z be z. But we're going to replace one of the parameters, since we have three, with something else. And we're going to do that by writing the equation of the cone in cylindrical. So in cylindrical, z equals square root x squared plus y squared becomes what? How do we write that in cylindrical? So z is still z, and x squared plus y squared is r squared, and square root of r squared is just r. So in cylindrical, the equation of this cone just becomes z equals r. So that can just tell us we can replace z with r. Or if you want, you could replace r with z and you get the same thing. But we'll replace z with r. So we're just going to be left with r and theta. And so x is r cos theta. Y is r sine theta. And z is going to be r, like we just said. And we also need the bounds for our variables. So r is going to go from what to what here? Well, conveniently, we have z equals r, and we know z goes from 1 to 3, or 0 to 3. And so that means r is going to go from 0 to 3, because z is equal to r. And theta, we go all the way around the z-axis. It goes from 0 to 2 pi. OK, so we have our parameterization. So d capital S, not the vector, we know is the magnitude of the normal, or magnitude of gr cross g theta. So really quickly, gr cross g theta. So g sub r is going to be cos theta, sine theta 1. And g sub theta is going to be negative r sine theta, r cos theta 0. And when we take this cross product, we get negative r cos theta negative r sine theta r. And we're not worried about orientation here because we're not integrating a vector field. We're just integrating a scalar. And we're going to take the magnitude anyways. So the magnitude here is going to be square root r squared cos squared plus sine squared. So that's r squared. So square root r squared plus r squared is square root 2r squared, which is root 2r. And believe me, that step, your life is going to be made a lot easier by using cylindrical coordinates instead of taking the partial derivatives there. Instead of doing it as a graph of a function and then taking the derivatives with respect to x and y, it's going to be kind of disgusting there. OK. Why is it the magnitude? So look, what we're integrating here, we're finding the surface area, which is the integral of a scalar function. Right, it's because we're doing d capital S, not d vector S. And remember, if you're integrating a scalar function, so it's d capital S is magnitude GU cross GV, whatever you call U and V, dA, and d vector S is the vector version of that. And that is if we are doing a vector field, but we're just integrating the function 1, which is a scalar function. And so whenever, if you're doing line integrals and surface integrals, if you're integrating scalar functions, you're taking the magnitude of the thing. So for line integrals, you're taking the magnitude r prime t. For surface integrals, you're taking the magnitude of the normal, the cross product thingy. Does that make sense? Like if we didn't take the magnitude also, that it wouldn't make sense, right? We'd be doing the double integral of a vector thing, which doesn't make sense in the end. So, okay. So we have the area is the integral of 1, just make sure that's a big S, ds, which is the integral. Okay, so we said r goes from 0 to 3, theta goes from 0 to 2 pi of 1, and then ds we said becomes root 2 times r dr d theta. And so we get, so r becomes r squared over 2. And when we evaluate that from 0 to 3, we get 9 over 2. So 9 over 2 times root 2. And then we get 2 pi from the other guy. So we get 9 root 2 pi. I did not, because that is not a piece of the cone. So that is not, you need to be careful with these questions too. When I say the cone, z equals square root x squared plus y squared, that is only the side here. If you forget about z goes from 0 to 3, z equals square root x squared plus y squared is just going to be the side of the cone. Be careful with the cones and cylinders, because unless we say we're including the top and bottom, or the top in this case, so like the top and bottom of a cylinder, the cylinder x squared plus y squared equals 1 is just the side bit of that. So be very careful. If it doesn't specifically say we're including the top, we don't mean, it's not assumed to be a closed surface. So yeah, be really careful of that. Yeah. The answer key says 27. Let's see. So I already found one wrong answer on the answer key. This is what you got? Okay. Okay, well, let's see. If we include the top, let me just, the top should be, no, that wouldn't be it either. Yeah, because the top just has area 9 pi. And so that wouldn't work out either. Yeah. No, it should be 9 root 2 pi. Where did we get the 27? Yeah, not sure where that comes from. Yeah, I am not sure. It should be 9 root 2 pi. But yeah, so y'all got that also? Okay, all right. Well, it should be 9 root 2 pi. There are a few small discrepancies from the answer key. Okay, what else would we like to look at? 2b. Okay. So we have a function of x and y. That is x cubed over 2y. And x is square root 1 plus v cubed. Y is u squared plus 3uv. Okay. And so b is, if u increases by 0.5. Okay, so I think we're assuming also from part 1. Yeah, we have to assume u equals 1 and v equals 2 for this to make sense. So we assume u equals 1, v equals 2. So if u increases by 0.5 and v decreases by 0.25, how much will f change? Okay, so this is a, so approximately. So this is going to be a differentials problem. So remember, the differential of a function of x and y is going to be okay, so actually this is a little more complicated. So if we think of f as a function of u and v, the differential of f is going to be the partial of f with respect to u times the change in u, du, plus the partial of f with respect to v times the change in v. So this is kind of a combination chain rule / differential problem here. Okay, so this would be straightforward. If f were already given as a function of u, but f is given as a function of x and y are each given as functions of u and v. So to calculate this df du and this df dv, we're going to need to use the chain rule. Okay. So for df du, so it's given as a function of x and y. So just to remind yourself, the way we do the chain rule is we have our function, or just think of f as our dependent variable. The intermediate variables are x and y. It's ostensibly a function of x and y, but these are x and y are both functions of u and v. And so for the partial of f with respect to u, we look at all the ways we can go from f down to u, and then we take derivatives down, derivatives at the nodes, and then multiply down, and then add across. So this is df dx, dx du. And then df dy, and then dy du. So that's going to be the partial of f with respect to x times the partial of x with respect to u, plus the partial of f with respect to y, times the partial of y with respect to u. And so just to remind ourselves, we said f was x cubed over 2y. Just so I don't have to go back again. And then x was square root 1 plus v cubed. And then y is u squared plus 3uv. OK. So partial of f with respect to x is 3x squared over 2y. And the partial of x with respect to u is what? So x doesn't involve u. So if we take the partial with respect to u, we just get 0, right? So then the partial of f with respect to y is going to be, so x cubed times, oh, sorry, no, going backwards, lol. Negative x cubed over 2y squared. And then the partial of y with respect to u is going to be 2u plus 3v. And then, so we're assuming u is -1 and v is 2. And so if u is -1, v is 2, then x is the square root of 1 plus 2 cubed. 1 plus 8, square root 9 is 3. And then y is going to be -1 squared plus 3 times -1 times 2. So 1 minus 6 is -5. And this is what we answered in part A. So let me just write this down. We should get 0 plus -27 over 50 times -2 plus 6, negative 27 over 50 over 25, so negative 54 over 50. Negative. Okay. Right? Wait. No, 54 over 25. Let me check the solutions here. What do we get for, is that what we got for the partial def with respect to u in part A? Got negative of that? Okay. Oh, yeah, sorry. That is positive. Right. Yep. So it should be negative 54 over 25, correct? And then df dv, of course, it gives a decimal, because why wouldn't it? So we get, so 3x squared over 2y times, so df dv is going to be 3v squared over 2 squared 1 plus v cubed. And then plus, so negative x cubed over 2y squared, and then times 3u. And so plugging those values in, we get, once again, 27 over negative, whoops, wait, what was it? Oh, no, I think I just said that was 0 before. Yep, okay. Yeah, so we got negative 27 over 10. And then, so 3v squared, so v is 2. And so we have 12 over, so 6 over 3. So that's 2. Plus, so negative x cubed, so negative 27 over 50. And then 3u is just negative 3. So we get 81 over 50, and then 54 over 10, which is negative 275, no, 270 over 50. And so we get, so negative 189 over 50. Yep, that's right. Okay. Okay. So we got our partials. All right, we got that from part A. Sorry. And then part B. So our df is going to be, once again, the partial def with respect to u times du. plus the partial of f with respect to v times dv. And we just plug in what we know. So our df du we said was negative 54 over 25. And then our du is, whoops, 1/2. And then our partial of f with respect to v, we said was negative 189. Honestly, we don't need to do this much simplification. You could just leave everything like you had here and save yourself quite a bit of time. So negative 189 over 50 times, so dv we said is 1/4. And so we get okay, so we could say this is 4 over 8. So we get negative 216 over 200 minus 189 over 200. And we get negative 405 over 200. Which is indeed negative, yep, 2.025. Yeah. Okay. Sorry, but the important bit is we're doing, you got to remember the differential formula. So df is just, you take the partial of f with respect to, if so u and v are changing, then we have du and dv, that's how much they're changing. And df is going to be the partial of f with respect to u times the change in u plus the partial of f with respect to v times the change in v. Does that clear that one up, Everett? Okay, what else would we like to look at? Or anything else that you would like me to talk about more? So obviously, you know, judging from this, and this is a good guide, the newer stuff is going to be heavily weighted. And it's easily the most difficult and most complicated and most time-consuming stuff. So make sure you understand So step by step, how to integrate directly line integrals and surface integrals. So remember that is just parameterize if you have to. If you're doing line integrals, d vector or dr is going to be r prime t, ds is going to be magnitude r prime t. If you're doing surface integrals, ds is going to be magnitude of the normal, d vector s is just going to be the normal, both of those, dA. And then go to your function, vector field or scalar function, replace x, y, and z with the parameterizations, and then et cetera, et cetera. Those all work the same way. So that's not too bad, but then sort of remembering if you're just given a line integral or a surface integral of a vector field, and remember the integration theorems only work for vector fields when you're integrating vector fields. So I can write that down again. So the process for doing integrals of vector fields, or sorry, line integrals and surface integrals of vector fields, sort of the process you should go through to see if you can use any of the integration theorems. So if you have a line integral of a vector field, first thing you check is it over a closed curve? So if yes, it is a closed curve, then you see, okay, am I in R2 or am I in R3? If you're in R2, you use Greens. If you're in R3, use Stokes. So remember, so you just are asked to evaluate either they'll say the work done by a vector field as you move along C, or just the integral of a vector field over a curve C. And remember, sometimes you'll see that as integral f1 dx plus f2 dy. Or sometimes if you're in R3, f3 dz, etc. That's another way of writing the integral of, just keep this in mind, make sure you kind of have these interchangeably in your head. The vector field f1, f2, f3. Just remember those two are interchangeable. Anyways, so yeah, if it is a closed curve, you're going to use either Greens if you're in R2 or Stokes if you're in R3. If you use Greens, you're going to turn it into a double integral over a region in R2. If you're in R3, if you're going to use Stokes, and you're going to turn it into a surface integral of the curl of f. But yeah, okay. So if you're not closed, then you check, is my vector field conservative? So if no, you just have to evaluate directly. Right, parameterize your curve, et cetera, et cetera. But if yes, you can use the fundamental theorem of line integrals. In other words, you find a potential function and evaluate at the endpoints. So where possible, we want to turn these line integrals of vector fields and surface integrals of vector fields we want to use an integration theorem where possible. And so if we have a line integral, if it's a closed curve, you can always use an integration theorem, Green's in R2, Stokes in R3. If it's not closed, if it's conservative, we can use the fundamental theorem of line integrals. If it's not, then we just have to evaluate directly. And I know I've said this before, but it bears repeating because it's really important, and this is a huge part of your exam. So you really need to be comfortable with looking at something and figuring out what integration theorems, if possible, you can use. Okay. So that works for all line integrals of vector fields. For surface integrals, we could either be given the integral of the curl of f. So you're given a vector field and you're told to integrate the curl of f over the surface. That's a dead giveaway to always use Stokes. To turn that into a line integral of the vector field, not the curl of the vector field, over the oriented boundary, the boundary of S. So if you have a surface integral of the curl of the vector field, 100% of the time you're going to use Stokes' theorem. However, if you are just integrating a vector field and not the curl of a vector field, then you have to see, you need to be closed in order, it needs to be a closed surface in order to use an integration theorem. So is my surface S closed? Whoops. If it's not, you need to evaluate directly. Nothing you can do. Right? Parameterize, et cetera, et cetera. If it is, though, you can use divergence theorem. Right? We turn it into the integral over the enclosed region of the divergence of our vector field. And it's just a triple integral. So I will say, okay, usually if your surface S is closed and you're just integrating a vector field, usually you have to just evaluate directly. There are some exceptions. Sometimes you can close your surface and use divergence theorem. But that is like less common. And usually, I would only go to that step if you try to evaluate directly and what you're doing is impossible to do. So if we had like, say this is our surface, say z is like 1 minus x squared minus y squared from z from 0 to 1 or something like that, or say that the bit where z is positive. If we gave you a really disgusting vector field that can't actually be evaluated directly over this, what we could be doing is saying, okay, what we want you to do is we want you to add this other. Say that's S. We'll say this is S prime. The bottom piece in the XY plane, the piece of the XY plane that lies on the bottom, you can add that say this is outwardly oriented, and then we'll make that downwardly oriented. when we add the two together, if we consider the two together, it's now a closed surface. And so when we do the integral over the top guy, what we want, which we may not be able to evaluate, plus the integral over the bottom guy, that's the integral over the entire closed surface. And so we can use divergence theorem. So it may turn out this we can't do, but this we can evaluate, and this we can evaluate. And so we can just say the integral of the thing we want is just subtract this guy from both sides, and that's what we do. That's probably a less likely thing to happen. And I would say only do that step if you can't evaluate directly, I would say. But yeah, so I would really, really be comfortable with this stuff. And then the rest of the stuff, anything you go through, obviously, on the final exam review from the older material, and you don't quite remember, maybe focus a little more on that stuff. But yeah, this stuff you need to be very comfortable with. And this is going to be the most time-consuming material, most likely. Because there are obviously usually several steps, and then it involves parameterizations and orientations, et cetera, lots of calculations for each of these things. So yeah. Any other general questions or questions you would like to look at? Using the final exam, yeah. I mean, so the final exam review gives you an idea of the material that's going to be. It tells you essentially what material is going to be on the final exam. So focus your energy on, for the older material, just the stuff listed here, I would say. Because there's a lot of older material, it'd be a little unfair to include stuff pretty far afield from what's included on here, but yeah. Okay. What else? Do we have any other specific questions? Surely there's got to be some others. Number 5, sure. So the region in the first quadrant of the xy plane, bounded by the circle x squared plus y squared equals 9. So we're in the first quadrant. We'll say that's our region D. And that's the circle x squared plus y squared equals 9, the piece in the first quadrant. So find the points in this region. Let me just make a note. So find the points in this region closest to and furthest from the point 1, 4. Okay. So, a couple things. Okay, so this is an optimization problem. And so we want to find the points that maximize and minimize a certain function. what is the function we want to maximize? What is the thing in words we want to maximize and minimize? Well, if we take a point xy in our region D, we want to maximize and minimize the distance from that point to 1, 4. And so the thing we want to do is we want to maximize and minimize. Technically, the function we want to maximize and minimize. Someone's mic is on. Technically, the thing we want to maximize and minimize is the distance from xy to 1, 4, which is square root x minus 1 squared plus y minus 4 squared. But we've seen this trick several times when we want to do the max and min of a distance. Usually it's easiest to do the square of the distance because they're going to be taking derivatives and it's much nicer to deal with that. And if you find the minimum, it's because the square root of the distance is always positive. And the square of the distance is also always positive. So if we, if xy is the point closest to 1, 4, then the square of the distance between xy and 1, 4 is going to be the smallest value of the square of the distance over everything in D. And if it's the furthest from 1, 4, then the square of the distance is going to be the largest among everything in 1, 4 as well. So we're just going to let the function we want to maximize be the distance squared. So we'll say this is the distance. We'll deal with the distance squared, which is just x minus 1 squared plus y minus 4 squared. That's what we're going to maximize and minimize over this region D. Okay. So that's piece 1. Part 2 of this is, okay, so this is, okay, so this is a closed bounded region in R2. So if you have a 2-dimensional region in R2, if you can describe this region using inequalities and not just an equation in x and y. So if I had a region I could describe just using equations, then I would use Lagrange to find the max and min on that guy. But if I have inequalities, then we have to do the finding a max and min on a closed bounded region in R2 thing. So really, this region we could describe as x squared plus, so the set of x, y, such that x squared plus y squared less than or equal to 9, and x is positive and y is positive. Right, we can't just say this is a set of points satisfying an equation. There's an inequality here. It's a 2-dimensional region in R2. So we do our thing where we find the critical points of f that lie in D in a region. That's going to give us a list of points. And then 2, we find the max and min of f on the boundary of D. I'm sorry. Yeah. Or remember, we do the thing where we check the corner points. Remember, the corners is just where like the pieces that we can parameterize separately come together. So the corners here would be just 0, 0, 3, 0, 0, 3. And we'll say this is C1, C2, and C3 are going to be the three pieces of the boundary. Find the max and min are just the critical points of your transformed value of f, transform function f on C1, C2, and C3. Okay. So let's do these. Let's find the critical points of our function in D. Well, that one's going to be easy. So remember, our function is x minus 1 squared plus y minus 4 squared. So we want to find the critical points, so we set both the partials equal to 0. So the partial of f with respect to x is going to be 2 times x minus 1. That tells us x has to be 1 at the critical point. And the partial with respect to y is 2 times y minus 4. And setting that equal to 0 tells us that y has to be 4. Okay, so we have the point 1, 4 is a critical point of our function, but we only care about it if it's in D. Is 1, 4 in our region D? So if we plug in the point 1, 4, is it going to lie in the first quadrant, A? And is it going to, is x squared plus y squared going to be less than or equal to 9? Is 1, 4 in D? No, it's not. It's going to be up here somewhere. Whoops. So we don't care about that point because it's not in D. Obviously, that would give us a minimum, the minimum distance being 0. But that point is not in our set, so we're not considering it. Okay. So 2. Let's look at the corners. Oops. And then we'll check C1, C2, and C3. We'll just take note of these points that we get, and then later we'll check the value of f at them and see which is the biggest and which is the smallest. Okay, so the first bit of the boundary is C1. We'll say that's going to be the left vertical line. So the set of points there are going to be x is equal to 0, y is equal to y. Y goes from 0 to 3. OK, so these points are the form x is 0, y is y. Y goes from 0 to 3. And so what we're going to do is we're going to look at what our function is, plugging in those points. Now it's just going to be a function of y, and we're going to find the critical points of that function. So our function was x minus 1 squared, y minus plus y minus 4 squared. So plugging in x equals 0, y equals y, we get y minus 4 squared. And we want to find the critical points of this function. So we take the derivative, and we get 2 times y minus 4, set it equal to 0. We get a critical point at y equals 4. But because 4 doesn't lie between 0 and 3, the range for y, we don't get any critical points on C1. So no points to check on C1. Oops. Why would it be +1? So when we, oh, sorry, yes. I see what, okay, yeah. Yep. That's the function. You're right. X is 0, so it'd be 0 minus 1 squared. You're right. Yep, sorry. I see what you're saying. Yep, the derivative is still the same, but yeah. Correct. Okay, so then we do the same for C2. So C2 is this bottom piece. Now that is y equals 0, and x is just x from 0 to 3. So these points are going to be of the form x0, where x goes from 0 to 3. And our function there is going to be, so we'll call that f prime 2 of x. So plugging in x equals x, y equals 0, we get x minus 1 squared plus 0 minus 4 squared, which is 16. So finding the critical points of that transform function, we get 2 times x minus 1, set it equal to 0. Whoops. And we get a critical point. Let me say it like this. So we get a critical point at x equals 1. Now x equals 1 is in the set under consideration. And so we check our function there. At x equals 1. And we get 1 minus 1 squared, so 0 plus 16. So we get 16. Another way of putting this is, so this is on C1, if x is 1, all the points have y equals 0. So since we're sort of considering all the points, let's not even evaluate the function there. Let's do this. Let's say that corresponds to the point 1, 0, and we'll check that at the end with the main function. So this lies on C1 and x is equal to 1. Well, y is equal to 0 on all the points on C1. So this is the point 1, 0. That is a critical point on C2. Sorry, C2. So C3, remember C3 is a part of the circle. X squared plus y squared equals 9. So if you want, since it's in the upper half or the right half, doesn't matter, you could say it's y is equal to square root 9 minus x squared. Y goes from 0 to 3. Or we could use Lagrange. And I'm going to use Lagrange. So our constraint is going to tell us the set of points we're considering. So that is the points on the circle, x squared plus y squared equals 9. That's our constraint equation. But we're going to consider x squared plus y squared equals 9, the entire circle. But we're only going to consider points that we get that lie on this piece. In other words, where x and y are both positive. So we're likely going to get another piece down here, a point down there. We're not going to consider that for this specific problem because we're not considering that piece of the circle. But if we get a piece up here where x and y are both positive, which we should, that would be the closest point. That point is OK. OK. So remember, our f of x, y, the function we're maximizing and minimizing, is our x minus 1 squared plus y minus 4 squared. OK, so we set up our equations. The partial of f with respect to x is 2 times x minus 1. And that's equal to lambda times g sub x. So that's lambda times 2x. And then the partial of f with respect to y is 2 times y minus 4 is equal to lambda times g sub y, which is lambda times 2y. And then we also need to satisfy the constraint equation. X squared plus y squared equals 9. OK. So just as a bit of habit, it's good to check lambda equals 0. So if lambda equals 0, that means 2 times x minus 1 equals 0. So that means x equals 1. And then 2 times y minus 4 equals 0, so y equals 4. But the 0.14 doesn't satisfy the constraint. And so we're not considering lambda equals 0. Oops. OK, so lambda equals 0 doesn't give us anything. OK, so we're going to assume lambda is non-zero. And OK. So then what we're going to do is we're going to write right. OK. So let's expand this out and get everything involving x on one side and everything involving the constants on the other. OK, so we can just we can cancel these 2's to make our life a little easier. And so we get x minus lambda x equals 1, bringing the 1 over. So that's x times 1 minus lambda equals 1. So in other words, we can rearrange our first equation to get x is equal to 1 over 1 minus lambda. And then we can rearrange the second equation to get y minus lambda y. So y times 1 minus lambda equals 4. So in other words, y is equal to 4 over 1 minus lambda. And those imply, since x is 1 over 1 minus lambda, y is 4 over 1 minus lambda. That implies that x, so y is equal to 4 times x. Right? Whatever value lambda is, y is going to be 4 times 1 minus 1 over lambda, which is x. We're going to plug this into the constraint, solve for y. And so we get, so for x, so sorry, we're going to solve for x. So we get x squared, oops, come on, dude. So x squared plus y, which we said is 4x squared equals 9. And so that is 17 x squared equals 9. X is going to be plus or minus square root 9 over 17, which is 3 over root 17. And I'll write this on the next page. Okay. So our points that we get from the Lagrange multiplier are, so x is plus 3 over root 17. And since we know y is equal to 4x, y would be equal to 12 over root 17. So that's 1 point. And then for x equals negative 3 over root 17, we get y would be 4 times that, which is negative 12 over root 17. But since our C3 has x and y positive, we have to throw that second guy out. And so this is the point we're considering. So this is our critical point, in other words, on C3. Okay, so we're going back to our list. All the points we accumulated, we're going to check the value of f at each of these. So we got no critical points inside D, so no points there. For the corners, we got 0, 0, 3, 0, 0, 3. We're going to check f there. We also got, on C1, we got no critical points. On C2, we got the point 1, 0. So we're going to check that. And then from this guy, we got the point 3 over root 17, 12 over root 17. OK. So since our function was x minus 1 squared plus y minus 4 squared, so 0, 0, we get the distance squared is 17, 3, 0, we get the distance squared is 20, 0, 3, we get the distance squared is 2, 1, 0, we get the distance squared is 16. And then this guy, you don't actually need to, I mean, you can calculate it if you like. It's going to be not super duper pretty, but notice clearly we're going to get some guy like right here, and our 0.14 is going to be like up here. Clearly that's going to be the closest guy. Sorry, that point is going to be, so that's whatever. The point's going to be like there. You can check it if you like, but whatever. That's going to be the closest point. So that's our closest point. And then clearly the furthest away point is going to be, oh, sorry, no. Do 3, 0. One where the distance squared is the largest. Whatever, let's check. Okay. Okay. It's not going to be super nice, but does everyone kind of see graphically? Clearly that is going to be the closest point. So what we were doing with the Lagrange thing was, if we extend this circle, we're finding the closest and furthest points essentially from 1, 4. And so what we're getting was, that's our closest point, that's our furthest point. And since the point 3, 0 lies on the circle, whatever that value is that we get here, sorry, 0, 3, it's still going to be smaller. Or this distance is going to be shorter, because 0, 3 lies on the circle, but we didn't get 0, 3 as one of these guys. So the thing is, the question just asked, what is the closest point? What is the furthest point? And so if you just said that is the closest, you would probably, a grader would probably say, okay, that's fine. You can't just pull that out of thin air. You probably don't need to justify it, but if you wanted to justify it, you could say, because by Lagrange, the closest and furthest points are going to be one of these two guys. And since 0, 3 lies on the circle in question, and we didn't get 0, 3 as one of the closest or furthest points on the circle, clearly this 3 over root 17, 12 over root 17 has to be the closest point. Because yeah, we're not actually looking for the distance, the minimum distance, we're just looking for the point which minimizes the distance. So you can save yourself some time and not actually have to calculate all that. Okay, but yeah, to kind of use that reasoning, you kind of have to know what you're doing with the Lagrange. Okay, what else shall we look at? But yeah, okay, so the sort of the important thing I want you to take home is need to be a little careful. So clearly, okay, we want to maximize and minimize a function for this question. That function is the distance to the 0.14. But if we're talking about distance, it's always easiest to maximize and minimize distance squared. Because when we take partials, things get nasty when we have the square root. Much nicer to deal with the distance squared. Okay, so point 1, maximizing and minimizing the square of the distance. Okay, point 2, this region here is a two-dimensional region, a two-dimensional closed-bounded region in R2. If you were just going to use Lagrange, you would be able to describe everything in all the set of all the points would satisfy an equation, but this set of points does not satisfy an equation. It's the region in the first quadrant. So in other words, y is greater than or equal to 0, x is greater than or equal to 0, bounded by the circle x squared plus y squared equals 9. So it's going to be the set of points x squared plus y squared less than or equal to 9, x greater than or equal to 0, y greater than or equal to 0. And if you see an inequality, you can't just use straight Lagrange. You have to do this thing where you find the max and min on the interior of D. Sorry, find the critical points in D in this region, and then we check the boundary. And so for the boundary bit, be mindful. So if you can write the entire boundary using a single equation, you can just use Lagrange for that whole boundary, but we can't do that here. We have sort of 3 pieces of the boundary, and we got to check all 3 of these separately. So if you have multiple pieces of your boundary, the easiest way is just to check the corners where those pieces come together. And so that's the 0, 0, 3, 0, 0, 3, 0, 0, 3, 0, 0, 3. And then we check for the critical points. So either use Lagrange on each piece of the boundary, or do what we did in C1 and C2. And if they're just like lines or like, yeah, I would say if they're just like straight lines or whatever, just say, okay, the set of all points on C1, that's x equals 0. So the set of points is just x equals 0, y is equal to y, and y goes from 0 to 3. And then find the critical points of that when you plug in the point 0, y into your function f. So then it's just a function of y, take the derivative with respect to y, set it equal to 0, and then see if that is a point on C1, et cetera, et cetera. Yeah, so we did that for C1 and C2. C3, we use Lagrange because it's a little more straightforward. So C3 is a piece of the entire circle x squared plus y squared equals 9. And using Lagrange there, what we're doing is we're finding the closest and furthest points on the circle x squared plus y squared equals 9 from the point 1, 4. And it's good to understand that's what you're doing when you're doing Lagrange on that bit. But keep in mind, we're only considering the pieces on C3, and that's where x and y are both positive. And so if we happen to get a point in Lagrange where either x or y is negative, then we got to throw it out. And that's what we did. Okay. Yeah, so that is some of the most complicated stuff from, I think that was either exam 2 or 3. That is the most complicated material on there. I would say that is stuff you should be comfy with, because optimization problems are pretty much guaranteed to be on the exam. Okay. What else? Okay, 4 or 6, we can do both. So number 4, so E is the ellipsoid. So the set of points x squared plus 2y squared plus 3z squared equals 12. So we want to find the points the point or points at which the function x minus 2y plus 3z squared is maximized or minimized. So we're going to find the max and min of this function on this ellipsoid. Okay. So basically, we have a set of points we're considering given by an equation. The set of points on the ellipsoid satisfying the equation x squared plus 2y squared plus 3z squared equals 12. And we want to find the max and min of a given function. So this is the classic setup for Lagrange. Because we have a function we want to maximize and minimize, whoops, that's that x minus 2y plus 3z squared. And we have an equation, a constraint equation. We have an equation telling us the set of points we're considering. So the constraint equation is our g of x, y, z is the x squared plus 2y squared, whoops, plus 3z squared equals 12. So remember, your constraint equation tells us what points we're considering. And since it's an equation and not an inequality, we can use Lagrange directly. Okay, so we set up our equations. Remember, the gradient of f is equal to lambda times the gradient of g. So we set f sub x equal to lambda g sub x, f sub y equal to lambda g sub y, f sub z equal to lambda g sub z. And then we have the constraint. So the partial of f with respect to x is 1. Lambda times the partial of g with respect to x is lambda times 2x. The partial of f with respect to y is negative 2. Lambda g sub y. Let me just write this down, etc. Lambda times g sub y is going to be lambda times 4y. And the partial of f with respect to z is going to be 6z. And partial lambda times the partial of g with respect to z is going to be lambda times 6z. And we also have to satisfy the constraint equation. X squared plus 2y squared plus 3z squared equals 12. Let me do this on the other side. Okay. So it's not necessary for every problem, but it's good just to quickly check. Lambda equals 0, does that give me any points? So can lambda equal 0? Clearly no, because from the first equation, we get 1 equals 0. Second equation, we get negative 2 equals 0, etc. Clearly can't. So lambda is non-zero. So we don't get anything from lambda equals 0. That's fine. So now we're going to assume lambda is non-zero. Okay. So clearly, 1 equals lambda. Okay. Different ways to go about this. But so we know 1 is equal to lambda times 2x. -2 is equal to lambda times 4y. 6z is equal to lambda times 6z. Which one of those three equations can we immediately get some information from about either x, y, and z or lambda? Which one of those three equations is the easiest? Right, the z one, right? So we get 6z equals lambda times 6z. So there are two things that can happen here. So we could rearrange this guy. We could divide both sides by 6. And then we can bring the lambda z over. So then pull the z out. So we get z times 1 minus lambda equals 0. So one of two things is true for all these equations. So either z is 0 or lambda is equal to 0. Oh, sorry, lambda equal to 1. One of those two things has to be true to satisfy this equation. And since all the equations need to be satisfied at the same time, all of the equations need to satisfy either z is 0 or lambda equal to 1. So let's look at these two things separately. So if z is 0, that satisfies the last equation. And it satisfies the first two because they don't involve z. It's fine. So if z is equal to 0, lambda can be literally anything. That's fine. So if z is equal to 0, sorry, let's break these up. So if z is equal to 0, then from the first equation, we get 1 is equal to lambda times 2x. Let's get x by itself and write it in terms of lambda. So if 1 is equal to lambda times 2x, x is equal to 1 over 2 lambda. And if negative 2 is equal to lambda times 4y, y is equal to negative 1 over 2 lambda, right? It's equal to negative 2 over 4 lambda, which is negative 1 over 2 lambda. Whoops. Okay, and so we know if z is 0, okay, z is 0, then x is 1 over 2 lambda, y is negative 1 over 2 lambda. What's the relationship between x and y? Right, y is equal to negative x, or x is negative y, either way you want to look at it. Okay, so we're going to plug these into the constraint. And solve for one of the variables. So z is equal to 0, y is equal to negative x. Yes, I will. I will, Nick. As soon as this becomes available, I'll post it to the YouTube. So plugging in at the constraint, we get x squared plus 2 times negative x, y is negative x, squared, plus 3 times 0, z is equal to 0, squared, is equal to 12. So we get x squared, sorry, plus 2 x squared. So 3x squared equals 12. X is equal to plus or minus 2. So what we do is we look at the first, this is basically always how we do it. We look at the first three equations, see if any of them give us definite information about x, y, z, or lambda. The third one does. So we know either z is equal to 0, lambda is equal to 1. So z equals 0 doesn't affect the first two equations. And then we use the first two equations to get a relationship between x and y. And then we plug in z equals 0, y equals negative x into the constraint, and then solve for one of the variables. OK, so we have the points. X is positive 2, y is negative x. So y is negative 2, z is 0. And then x is negative 2, y is negative x. So that's positive 2. And z is equal to 0. So we get those 2 points from z equals 0. OK, if we get lambda equals 1, so if lambda equals 1, that does affect the first two equations. What does that tell us about x? Oops. So the first equation says 1 equals lambda times 2x. So if lambda is equal to 1, x has to be equal to 2x has to be equal to 1. So x is 1/2. Similarly, that tells us y has to be negative 1/2. Because negative 2 has to be equal to lambda times, which is 1. Negative 2 equals 4y. Y equals negative 1/2. Z we're not sure about yet. So we plug z into the constraint equation, along with x equals 1/2, y equals negative 1/2, and then solve for z. So x equals 1/2. So 1/2 squared plus 2 times y, which we said is negative 1/2 squared. Not sure about z, but we're going to solve for it here. So this tells us 1/2 is squared is 1/4. 2 times 1/2 squared, oh, sorry, is equal to, plus 3z squared. So 2 times 1/4 is 1/2. So we got 3/4 plus 3z squared is 12. We can divide everything by 3 if we like. And so we get 1/4 plus z squared is equal to 4. In other words, z squared is equal to 15 over 16. So z is plus or minus square root 15 over 4. Yes. OK, so we get the points. So in all of these, x is 1/2 and y is negative 1/2. But we get z is square root 15 over 4, and then we get z is negative square root 15 over 4. Oh. OK, so those are the set of points we're considering. We're going to find the one which maximizes our function, and the one which minimizes our function. So f of 2, negative 2, 0. Remember, sorry, our function was x minus 2y plus 3z squared. And so f of 2, negative 2, 0 is going to be 2 minus negative 4. So that's 6. F of negative 2, 2, 0 is going to be negative 6. F of 1/2, negative 1/2 square root 15 over 4 is going to be, so 1/2 plus 2 times -1/2, or sorry, minus that. So 3/2 plus 3 times 15 over 16. And I'll simplify that in a sec. And then f of 1/2 -1/2. That's true for both of these because we're squaring that. Those are both give the same thing. And so let's compare that to the other two guys. So that's 2469 over 16. And then just for reference, 6 would be 96 over 16. Yep. Okay, so the point which maximizes is going to be the 2, -2, 0. And the point which minimizes it is going to be the -2, 2, 0. Yep. Okay, let us see. Answer key. Root 15 over 2. So let's make sure we didn't make a mistake here. So lambda equals 1. So we got the 1/2 -1/2 times 3z squared so that's 1/4 plus 2/4, right? So that's 3/4. Divide everything by 3. So we get 1/4 plus z squared is equal to 4. I think there was probably a mistake there. Yep, we're definitely right. Oh, and then we take the square root. Yes, I'm sorry. Nope, I don't know why I squared in my head there. Sorry. Yep, okay. My fault. My fault. I squared and then unsquared for some reason. Yeah, sorry about that. Okay, I thought that was a little weird. Okay, so then we plug that in and we get, nope. So 45 over 4, right? And so then this is 51 over 4. And so then 6 would be 24 over 4. So clearly, sorry, yep. So our max is this guy, which happens at 1/2 -1/2. And then either plus or minus root 15 over 2. And then the min is at the -6, which is -2, 2, 0. Sorry about that. Yeah. Yep, that is the answer key is correct. Yep. My bad. Okay. So that's 4, and then I believe we also wanted to look at 6. I can look at 6 as well. So number 6, so the production function, I love these problems for some reason, is so 3/4 k to the 1/3 L to the 2/3 The unit of capital costs 2,000. And a unit of labor costs $3,000. We have a monthly budget of 20,000. Oops. So unit of capital costs. Let's just do everything in thousands. So in thousands. Solution for number 26. Oh, do I? Let me see. Number 26. Let me check that real quick. I do. No. No, actually, so let me show you. So careful with that. Let me do a separate thing. So we have the bit of the sphere above z equals 1. And so remember with, sorry, okay. Yeah, it shouldn't be 0. Yeah, so this is my fault. So remember for rho, I actually did make a mistake, but it wasn't that one. Yeah, okay. So for rho, remember, just draw a line from the origin through your thing. And look at the surfaces it hits and write them as rho equals something. So this guy, yeah, actually, I do need to adjust this. This is rho equals 3. Sorry, rho equals 2, the sphere. And this guy is z equals 1, which is rho cos phi equals 1. So rho would be 1 over cos phi. And so rho should actually go, sorry, this is my fault, 1 over cos phi up to 3. Oh, you parameterized with cylindrical. You could do that. You could do that. Yeah, I'll have to. Let's do that really quickly. But let me do it using the spherical here. Okay, so we're integrating 6 as the divergence. So rho squared sine phi d rho d phi d theta. So we said rho goes from, sorry, 1 over cos phi up to 2. Phi goes from 0 to it's pi over 3, I believe. And theta goes from 0 to 2 pi. Okay, so we get 2 rho cubed. So when we multiply through, we should get 8 sine phi. Sorry, times 2. So 16 sine phi minus 2 sine phi over cos cubed, so cos to the negative 3 phi. And then we integrate with respect to phi. So we should get, so negative 16 cos phi. And then this guy should go to so minus cos to the negative 2 phi from 0 to pi over 3. So that's 8 minus, so 1 over cos squared so that should be 4 minus 1. Yep, and that's where we get the 5. Okay. And so the integral from 0 to 2 pi of 5, that's where it comes from. Okay, sorry. Sorry. That is indeed the 10 pi. Yep, okay. Yep, I need to go back and change that. Thank you for pointing that out. Okay, yeah. So cylindrical or spherical should work in that case. Sorry about that. So I'll work that up. But I am certain the one where I get the sign difference, I am certain that one is correct. And the answer key was wrong on the sign on that one. Yeah. I think they just mixed up the orientation. Okay, so, okay. This is in thousands. So K is 2000. Let me do this one real quick. L is $3,000. And the most we can spend is 20,000 per month. Okay. So we want to maximize our function here. So what we do is we're going to get a relationship between K and L by taking the partial derivatives. We're going to find the critical points. Oops. So dptl, or let me say dpdk. So dpdk is 1/4 K to the negative 2/3 L to the 2/3 and dpdl is going to be 1/2 K to the 1/3 L to the negative 1/3. And so to maximize profits. Okay, so the max is going to happen where the partials are equal to 0 at the critical points. And so this is So 1/4, we can write the first guy as 1/4 L over K to the 2/3. And the second guy as 1/2 K over L to the 1/3. Does everyone see that? So K to the negative 2/3 is 1 over K to the 2/3. And so we can just write that as L to the 2/3 over K to the 2/3, which is just L over K to the 2/3. Or you know what? Let me write it like this. This is a little. This would be. That's not actually helping any. Okay, so we know those are both equal to 0. So we're going to set them equal to each other. So it's equal to 1/2 L to the, no, sorry, that's 2/3. And so we multiply both sides. No, I got that mixed up. It's K over L. Okay, so we can multiply both sides by the L to the 1/3. And both sides by K to the 2/3. And we get 1/2 L is equal to, 1/4 L is equal to 1/2 K, or in other words, L is equal to 2 times K. So in fact, actually what we wrote is not technically true. Yeah, what's going to happen is we're also going to have like stuff not existing. But at critical points, either it's 0 or it doesn't exist. So we can forget about that bit. But we have this relationship between L and K. And so then we just go back to our production equation. We know we have 20,000. That's the max we have. And then we replace L with 2 times K. So 3 over 4 K to the 1/3 times L, which is 2K, to the 2/3. So we have K to the 1/3 times K to the 2/3 is K. And then 2 to the 2/3 is K. And so K is just 20 over that. So is there a nice way we could simplify this? Not really. We'll leave it like that. So K is 20. Oops. Over 3/4, 2 to the 2/3. You can simplify that if you like, but like it's still a correct answer. And L is 2 times that. and that will maximize our profits. So let's see. 10/3 and 40/9. Okay. So our what did y'all get for this one? Does it look like this disagrees? You got what the answer key said? Okay. Oh, hang on, did I mix things up? Nope, that's right. Okay. Yes. Okay. Yeah. Yeah. Okay. Yeah. Oh, you're absolutely right. Okay. Yeah, we did the wrong constraint. Yep. Nope, you're exactly right. You're right. Sorry. Yeah. So we yes. Yes. Yeah. Yep. So that's the production, not the money. That's what we're maximizing, minimizing. We're being bullish here. Yep. Okay, my goodness, guys. Yeah, okay, we were taking that is my fault. Okay. Sorry. Yeah, this is clearly Lagrange. Yeah, we want to use Lagrange here. So our budget is going to be our constraint. Sorry, so we got 2K plus 3L is, oops, 20, right? And so we get this is equal to, sorry, the partial of G with respect to K. So that's 2 lambda, and this is 3 lambda. And then we go from there. Yeah. So we can multiply both sides by k to the negative 2/3. So yeah, lambda equals 0 is not going to work in this case. Because if lambda equals 0, either k or L has to be 0. And in both cases, one of these equations is going to be off. Oh my God, you guys, I'm so sorry. Okay. And so we get L to the 2/3 is equal to 8. No, you know what? We're going to set them both equal to lambda. That's the obvious play here. Okay, so we divide both sides by 2. So we go 1/8. L to the 2/3 over K to the 2/3 is equal to, and then from the second equation, we get 1/6 K to the 1/3 over L to the 1/3. Because those are both equal to lambda, since lambda is not equal to 0. And so we get 1/8 L is equal to 1/6K, or in other words, L is equal to 4/3K. And then plugging that into our constraint, we get 2K plus 4K is equal to 20. So K is equal to 20/6. So K is 10/3. And then L is 4/3 times that. My goodness, I am so sorry about that. And that's where the max happens. That was supremely embarrassing. Yes, this is clearly you want to use Lagrange here. Maximizing, minimizing a function subject to a constraint. Well, okay. All right. Anything else before I end it? I could answer one more question if y'all have anything else. If not, then I will go and write up the solutions. All right. Well, good luck on your exam then, and it's been a great semester, and have a great summer, and yeah, good luck. Have a good one, guys.